Welcome to 41st lecture in the course of Industrial Engineering and Operations Research. We have been discussing operations research. In fact, we delivered 10 lectures on operations research, and particularly I discussed linear programming problem. Linear programming problem can be solved by graphical method as well as it can be solved by simplex method. We discussed special cases of the simplex method. We also discussed dual programming problem. Now, few lectures will be devoted on transportation models. Actually, it is also a special type of linear programming only. But since it has got a specific characteristic, that's why this is considered a separate class of problems, and that means transportation models. We have already done one special class of problems. Those are called assignment problems that we discussed long back when I was discussing the industrial engineering portion. Now, let us see that what is a transportation model, how this problem is special. So, as you know that transportation means sending things from one place to other place. I am starting with one example. Suppose some special items are produced at factories at Patna, Guwahati, Mumbai and Hyderabad. These are the cities. Okay. So, Patna, Guwahati, Mumbai, Hyderabad, these are the cities. Okay. Patna is one city in Bihar, Guwahati in Assam, Mumbai in Maharashtra, Hyderabad in Telangana. These are the cities which have 4 factories. So, there are total 4 factories and they have to be sent to destinations. So, destination is Lucknow, Delhi, Jaipur, Chennai, Kolkata. These are also cities. So, from Patna, one can send item to Lucknow, one can send to Delhi, one can send to Jaipur, one can send to Chennai, one can send to Kolkata. Similarly, from Guwahati, one can send to all 5 places. Now, supply from each factory means Patna factory produces 3000 items, Guwahati produces 6000 items, Mumbai produces 4000 items and Hyderabad produces 5000 items. These are the items which are produced. But demand is in Lucknow, it is only 2000, Delhi it is 7000, Jaipur it is 4000, Chennai it is 1000, Kolkata it is 1000. So, this is the demand. Now, we have indicated, now distribute. So, these items are produced in factories and distributors are located at Lucknow, Delhi, Jaipur, Chennai and Kolkata. Supply and demands of items are indicated in table. Note that the factories have capacity to produce 18,000 items. You see, they have total 18,000. That means if you sum that 3,000, 6,000, 9,000, 13,000, 15, 18,000. So, 18,000 is the total supply. That means total production of items is 18,000, but our demand is only 2 plus 7, 9 plus 4, 13, 14, 15. Demand is only 15,000. So, it is unbalanced actually. And transportation cost of I have given of each item is proportional to distance it travels. Suppose I have done like that. So, I knew that from Google I have found the distance like Patna to Lucknow 610 kilometer, Guwahati to Jaipur it is 1946. So, I have put all that type of things. So, let us say you assume that transportation cost will also be proportional to kilometer. Okay. So, the road distance from factory to distribution center in kilometer are indicated in each cell. Now, your goal is to minimize the transportation cost. That means, in what manner you should send the items to different places. That means, from Patna should I send to Lucknow? Maybe it appears that maybe even Kolkata is nearer 580. So should we supply how much items? It makes 3000 items. But if Kolkata needs only 1000, so maybe 1000 I can give to Kolkata, remaining I have to give to other places. Like that we have to do that. So we have to minimize the transportation cost. So this is a problem. This type of problem is called transportation model. Okay, we have to make a model, that is transportation model. But here as we discussed, that this is there, it is unbalanced problem because demand and supply are not equal. As I said, that you just see that here 18,000 is the total supply, demand was only 5,000. So what should we do that? That means we can make some dummy destination. Okay, we can make dummy destination. Sometimes we may have to make a dummy supplier, but here supply is already very high, so you need not make any dummy supplier. But suppose supply is less, then you have to make dummy supplier. So here it is dummy destination. So suppose there is another city called dummy. Okay, that means it is not a real city, just name. And distance of this from Patna to this one, I have put 0, Guwahati to dummy 0, Mumbai to dummy 0, Hyderabad to dummy 0, because it doesn't matter. Actually, if you give anything to this, it will not add to any cost. Okay. So here dummy destination requires 3000. Okay. Now this problem will be fully balanced, because if you add the supply, so this becomes 18,000, and if you add the demands, it will also become 18,000. 2 plus 7 plus 4 plus 1 plus 1 plus 3. So this becomes 14, 15, 33, and this becomes 18. So 18,000. Now this type of, so this, once this has become a balanced problem, then it can be easily solved and we can make algorithm. But what I am telling that, so a standard problem will look like this. Okay, just like we have shown that standard problem will look like this. I am showing the characteristic. Here I am writing the standard problem in the form of a matrix. Okay, this side you have maybe factories and this side you have destinations. Okay, so you can say destinations. Okay, this is yeah, destinations. Nations. Okay. So you may have n destinations and then suppliers. And here you may have, how many suppliers you may have? You may have m suppliers. So m supplier and n destination. And in each cell, I am putting the unit supplied from supplier I to destination j, that is represented by xij. So x12 means supply is from factory 1 and destination is city number 2. Similarly, xmn means supply is from factory 5 and destination is city number n. Like that we have put, and corresponding demands are given, because in each column represents one destination. So demand B1, B2 and Bn, like that. And similarly, availability is given like this: A1, A2, A2 and this is AM. Okay, so this is not 2 should not be there, that is basically AM. You can say this is AM. Okay, so you can have this type of thing. So you have basically availability also, and this is also, and if it is a balanced problem, then sum of sigma i's will be equal to sum of sigma bi, that is also there. But here I have not indicated the cost associated with each cell. There is a cost, that means cost of transportation from one cell to other. So this I have not indicated. Maybe you can make some kernel, here you can say 30, here you can say 40, like that you can make whatever way you can distinguish. Otherwise you can make a bracket, but I can make a square type of thing. So this is the standard problem. Okay. So now can we do it by linear programming way? Let us see that, can we do linear programming way, how it is equivalent to linear programming. So our goal is minimize the transportation cost. and we can assume that these are the units supplied from various suppliers to various destinations. If there is no supply from one supplier to another destination, then that cell will become 0. Okay, so general case we assume that all xi's are filled. So minimize I is equal to 1 to m, j is equal to 1 to n, Cij xij. Cij is the cost of transportation from destination I to say supplier I to destination j, supplier I to destination j, so Cij xij. So that means you sum that. In effect what we are doing, that we are going j is equal to 1 to n column wise, and this is I is equal to 1 to m. For each row there are n columns, so I have written j is equal to 1 to n and then Cij into xij. If I do that, that will be the total cost. That cost has to be minimized such that j is equal to 1 to n, xij is equal to ai, and I can be 1, 2 to m, 1, 2 and then after that m. So such that xij is equal to sum of this one. So that means in each row there are n columns, so I am summing them together and making it equal to that corresponding basically supply. Okay, you can say x11 plus x12 plus x1n is equal to a1. So you have got like that. Similarly, I is equal to 1 to m, xij is equal to bj. That means for each j is equal to 1 to 2n, means these are in destination cities. For each destination city, that supply from various factories is added, and this is made equal to that. So this is equal to this one, but xij should be greater or equal to 0, because you cannot supply negative quantity. So naturally it must be greater or equal to 0, and I is equal to 1 to m. These are m. You can say factories, m factories, and you can say j is equal to destinations. Okay, you can say destinations. So for consistency, you know that if we have written the equation like that, it is obvious that I is equal to 1 to m, ai should be sigma j is equal to 1 to n bi. It is obvious because the way I have written, because if I say this much I have written, and if I do that this one, I sigma I is equal to 1 to m, and this is ai. So instead of ai, I can write sigma j is equal to 1 to n xij. This will be ai, and if I want to write bi, that is j is equal to 1 to n. So we can say j is equal to 1 to n, and this is in each one I is equal to 1 to m, and I can say bj. So instead of bj, not bj, rather I will simply say this is xij is equal to, this is not sigma ij, rather it is sigma I is equal to 1 to m ai. Okay, that is I hope. So this is yeah. So this one you have done like that, and this is equal to sigma j is equal to 1 to n, and this is bi. So you can compare these two things, you can see that these two things are basically same. So therefore this has to be there. So that means by way of that my formulation also this condition has to be satisfied, then only you can write in standard LP form. That's why every transportation problem should be balanced. If it is not balanced, you have to add dummy destinations and dummy factory depending on the requirement. Okay. So if we have written this type of problem in the linear programming form, then solving this is not a problem. How many decision variables are there? Each xij is a decision variable. So maybe that, so therefore decision variables are m into n. That means m into n. Suppose there are 3 destinations and 5 factories, then means 15 variables. So that means these are the decision variables, equality constraints have been given. So you can use any standard software and you can solve this LP problem very easily. You can even use the MATLAB programming. In MATLAB you can write this one, there is a procedure to give there that this is the C matrix, coefficient matrix, this is the supply, that means right hand side demand, and then you have to put all those type of things, add dummy demand, and then after that you can actually zeros and you can have this one, you can put the supplies and you can have this thing and you can make that A equivalent like that, and then you can solve by linprog. In there is a function linprog in MATLAB that can be used for solving this problem very easily. And in linprog, as per that syntax of the linprog, you can give the data and then after that this can be completed. So you can get the solution and transportation model has been solved. So you see that in fact solving it is not a problem nowadays. You can of course solve it by simple linprog or any other that linear programming software. That is not an issue. Main thing is that you have to formulate the problem properly. And in fact, let me tell that it is not only that it is for transporting one good to other, you can use it for different purpose, means same type of model. Suppose I have the thing that suppose there is a, these are maybe Patna, Guwahati, Mumbai, Hyderabad, these may be coaching institutes, and instead of Lucknow, Delhi, Jaipur, Chennai, Kolkata, they may be that students of class 9, this may be class 10, this may be class 11, this may be class 12, and this may be BSc, okay. These type of, and it is known that which coaching is in what degree suitable for that, okay. So you can put some rating type of thing, okay. You can say that class 9 boys, if we assign to coaching at Patna, then it is about that 610 something rating. Class 10 boys, if they are assigned to this one. Now the thing is that you assign the students, and students are given class 9 they are 2000, class 10 there are 7000, class 11 there are 4000. Now you assign them in such a manner so that overall satisfaction or overall performance is maximum. So instead of minimization, it is a maximization, but you can always convert a maximization problem to minimization problem. You can multiply it by minus, everything can be made minus. Instead of 6110, you can do this one. Similarly, it may be that you can consider instead of these distributor factory, you can consider these may be the workers, okay, worker number 1, 2, 3, 4, and then this may be jobs, and you know that each worker quotes different amount of money for each job, or you know that very well that she suppose Patna worker will make some Lucknow type of item, but cost is he charges 610 rupees per unit, and these are the capacities that that how much the job one is required and how much that person can make, okay. That say Patna worker can make only 3000. So the question is that how you should allocate jobs to that workers so that your overall cost is minimized. So such type of problems can be done. So there is no transportation, but even then they will be called transportation model. It is basically category. And we already discussed assignment model where we were assigning that worker to job, but there was one worker and one job. But here there may be one worker and he can do many jobs. So how to do that? Okay. So you can, so issue is that solving is not a big problem. Main thing is that how to do it formulation, okay. Now let us discuss that if it is a linear programming problem, then we can write a dual of this transportation problem also. Suppose this is primal, minimize this much, such that j is equal to 1 to n, xij is equal to ai, I is equal to 1 to m, sigma xj is equal to b, j is equal to 1 to n, xij greater or equal to 0, and these things are given. So how can we convert into dual form? First, my minimization becomes maximization, you know very well, and associated with this I can associate some variable ui, like we can, and here I can use vj. I could have used the same symbol, but I am telling that ui, and let us say that here I am using that vj. Okay. So that means with ith constraint I put ui. You can say ui is a dual multiplier or shadow price or unit worth of resource of that constraint. So minimization becomes maximization, and sigma I is equal to 1 to m ai ui, because as I said ai ui, and plus sigma j is equal to 1 to n bj vj. So that means objective function, and such that now constraints, because there are basically m into n variables corresponding to each variable, you have to write basically this thing I is equal to 1 to m and j is equal to 1 to n, and you have to write constraint this one. So you focus on that coefficient of that particular, that ij. So it is basically here ui, and then here you say plus vj, and this should be smaller or equal to cij, because it is maximization problem. So it should be this one, and u and v are unrestricted, but you get this type of condition that in dual problem ui plus vj should be smaller or equal to cij. Okay, that type of thing is there. So it gives a, you will understand later on, it will give you a type of clue in understanding the things, but I am telling that it is possible to write a dual of that transportation model also. So u and v are unit worths of resource, and now primal constraints are basically we can write in this form also, in the different form x11, x12, x1a1, x21, a2, and like that we have written x11, and then we have put this type of thing. We can naturally write in the form of matrix also with lot of zeros. Okay. So what I am telling, that when you are solving that, you are seeing that total constraints are basically m plus n, right. There may be m sources, and there may be n destinations, m suppliers, n receivers. So total constraints are m plus n, but effectively their total constraints are m plus n minus 1 equality constraint, because you also have that one condition that a11, a2, m, this equal to sum of these things is equal to this thing. Okay. So that means you have that one condition. Okay. So by that condition you have this type of thing. So effectively you have m plus n minus 1 independent one. So therefore you can make a basic feasible solution which should have m plus n minus 1 basic variables. So a transportation problem always has a solution, there is no difficulty, because this is equality constraints, but there is exactly one redundant equality constraint. When any one of the redundant constraint is dropped, the remaining system of m plus n minus 1 equality constraint is linearly independent. Okay. So that means this one. So we can do that basic feasible solution. So that means we can find out the basic feasible solution. So what I am telling, that although you can solve the transportation problem by means of like a linear programming problem, simply put use lin prog function, or you use any online tool for LP solver, but we will be telling some other methods which may be more efficient in solving that. That is what we will be telling, but the basic concept essentially will be same, that basically it is something there is a similarity with simplex. Basically we are doing simplex operation only, but in a different way. So like in the simplex one, we need a initial basic feasible solution. Here also we will be needing initial basic feasible solution, but same thing can be written nicely in the form of matrix itself. So, total m plus n minus 1 xij are basic. That means they may be 0 also, but they may be non-zero also. The remaining are non-basic and taken as 0. So, remaining are non-basic and they are taken as 0. Some basic variables may be 0. I am telling that some basic variables may be 0. It is not that they cannot. Then we have degenerate basic solution. Even then you have to write and designate them as a basic variable and say that its value is 0. So, to make the initial basic feasible solution, also there are many methods, and particularly we will be studying 3 methods. One is called north-west cardinal rule. Okay. What is north-west cardinal rule? Because here in transportation problem we represent in the form of matrix. Okay. So, this is like that. As you have seen that there may be 4 destinations, 4 suppliers, 4 destinations. So, we have got 16 cells. So, this cardinal is called north-west cardinal because it is in north side. This is north, this is north, this is south, and this is east, and this is west. So, north-west means it is like this diagonal one. So, this is north-west. So, you start from here, that means you assign as much as you can do to this cell, as much as you can do, seeing the supply and demand you assign that, and then you keep moving either sideways towards right or towards bottom, you move from that. That is why it is called north-west cardinal rule, because it starts from north-west cardinal. Another method is called least cost method. It is a heuristic method, that is also heuristic method. So, heuristic here means that you know that based on your understanding reasoning, okay, without going much into mathematics, and you assign that least cost method means the cell which has minimum cost, you assign maximum quantity to that first, and after that it gets assigned, then you go to next cell. So, therefore, you assign based on the least cost. And then we have got Vogel approximation method. This is, we will discuss this also. Okay. North-west cardinal least cost method. Vogel approximation is based on some type of penalty that we will be discussing, that will become clear to you, and that we will be discussing that. So, this is what. So, maybe from the next class I will be discussing these methods to make the initial basic feasible solution, that means one solution, and we will start from north-west cardinal rule. Okay. But just for change, I am now giving you some quiz question, etc. Suppose we had to make a dummy destination to balance transportation model. Suppose, is there surplus at the source or shortage? That is the question. So, we had to make a dummy destination, that means destinations are less. So, that means there must be surplus at the source. That is why we have to make some dummy. Dummy means, of course, actually it is not that that amount will be dumb to dummy. There is nothing called dummy. It is only thing that much amount will remain. Okay. So, that means we have to say, is there surplus at the source or shortage? So, naturally there is surplus. And we had to make a dummy source to balance transportation model. Suppose we had to make a dummy source, one more source of production should be there. So, actually it is not there, but we will be assuming that okay, there is one more source. So, is there surplus at the source or shortage? Naturally there must be shortage. That is why we are making one dummy source. So, in practice what will happen, that some destinations will not receive that proper quantity, because naturally that suppose they will get something from dummy source, that means they will not get. So, this is what that this one. So, that such type of questions can come. So, transportation scheme with a dummy destination. See, this is source 1, source 2, source 3, and destination is destination 1, destination 2, and dummy. And so, you see that here sources are producing 3000, 1000, 900. So, therefore, total is how much production is there together in 3 factories, that is 4,000, 13,000. And how much is the demand? 2,900, 1,500 in two sources. So this much comes only 4,400 plus this is the thing. And if you have say 3,000, 4,000, 4,900, okay. I just thought it is 9,000, but it is not 9,000, it is 900. So let me just erase this and say 3,000, 1,900, this is 4,900. It is 4,900 and it is 2,900, 1,500. So demand is only 2,900 plus 1,500 means 4,400. So that means demand is only this one, but I am producing 4,900. So make that means 500 will not be sold. So instead of telling that 500 will not be sold, you can say 500 will be taken by dummy destination. Dummy, a location called dummy will issue these 500 items. So you put it 500, but you put the cost associated with this as 0, this is 0, this is 0. If source 1 to destination, if 1 unit goes, 1 per unit cost is 100, okay. That means understand that it is per unit only, no? Not the total cost. Total will depend how much you assign. So now we want to put constraint that source 2 must supply all the items. Suppose we put a constraint that, suppose some problem has been made in a different way. We put that source 2 must supply all the items, suppose we say. So then what should I put it? Then put a high number in the second row of dummy column. That means this one. So suppose instead of 0, if I put it something here 10,000. So this cost becomes very excessive. So therefore you have to minimize that. So automatically the algorithm will try to assign 0 to it. Because source 2 will be source 2 must supply. Now we want to put that hence put a high number. So that means it is so source 2. So that means if we put this one, so they automatically any source 2's thing will not be assigned to dummy. So naturally that it will be assigned either here or here. That means source 2's everything will be sold out, okay. It's 1,000 pieces will be sold out, okay. So that means we can put like that. So that is how that we can adjust that type of thing, that whatever we want. Now, if you have put here 10,000, tendency will be that here nothing will be this one. So this is what this one. So now how do you solve that? Formulate the problem in a matrix. So find an initial basic feasible solution and optimize the solution to minimize total transportation cost. That is the third step that we will be discussing. But first we will discuss that how to obtain initial solution, okay. So these type of things will be there, and this one, so this we will be discussing now in the next class. Next class we will be telling this step, formulate the problem in a matrix, that you have already seen that this is a problem, it is formulated like a matrix, okay. Then initial base feasible solution. So in the next class I am going to tell transportation problem, finding the initial feasible solution by northwest corner method, okay. That will be told, and then further will be optimization of the solution to minimize total transportation cost. So only this much for today. Thank you very much for your kind attention, okay.